All right, good morning. I hope people had a good weekend. Not too many ski crashes, although I've heard there was at least one for a snowboard crash. Um, so yeah, and now, by the way, you've had some experience playing with some of the dynamics that happen in chaotic systems. You had a little bit of experience programming up 1D map, and you've had some experience in playing with it and seeing what happens. And I wanted to mention that my problem sets are not highly prescriptive with one right answer that you have to get, and it's 1.732. The one that you saw that you did last night or over the weekend is very typical for me. There is learning and there is thinking in exploration. So I don't say try R equals 3 and R equals 4 and tell me what the answer is. I say explore, play with R and tell me what happens. Because again, there is, when you're playing with R, you turn R up and something happens or it doesn't happen. You're using your brain and your knowledge of dynamical systems to decide whether that change is meaningful and what it is that you're seeing. So that's why my problem sets are designed the way they are. And it can be a little uncomfortable at first because it's probably quite different from some of your other classes where there is, a single right answer and it has a number to it. Mine is more about thinking in pictures and so on and so forth. So today we're going to build on that. We're going to talk more about the dynamics of maps. But first, a couple of announcements. There is a problem set due today. Anytime today is fine. Don't let it trash your day and turn it in at 11:59. It's not worth it. So, just get it in. I'm more interested in the thinking. So for example, if you cannot get it to work and you have a picture that doesn't look right, just turn in that picture and say, I know this picture isn't right and it really should look like that. You'll get most of the credit. It's the thinking again is what I want in this class. There's a problem set due next Tuesday. Its handout, along with every other handout in the class, is posted on my private webpage. That being said, please turn in your work on Canvas. You will also get your graded work back on Canvas. I only use Canvas in this course for the stuff that's private to this course because I have that public webpage that I want everybody to be able to access. And so all the handouts are on that public webpage. It's colder today than I thought it was. Any questions on logistics? And again, remember, I can't track the chat because I'm working on a small screen. So if you have questions, sing out, please.
Should we turn in as a PDF or a docx, or is there any?
Doesn't matter. PDF is easier, but actually, yeah, PDF is easier because then I can use the annotation tool on it. If you would, that would be great. Thank you.
I have a quick question about when we go back in person. Are we still going to turn in on Canvas or will you want hard copies?
On Canvas, just
Okay.
make things easier. This is the first year I've done that, but I don't want to change in midstream, but thank you for asking that. Any other questions? Okay. So let me switch cameras to let's go there and go there. Problem set 1. And get this camera to, there we go, I did. I just wanted to do a little bit of review, and this should be pretty quick now that you've all at least started, I hope, this problem set. There are lots of different ways we plot behavior in dynamical systems, and you'll see another one today that's called the bifurcation diagram. In a map, remember, time is discrete. Time proceeds in integers. Time goes in clicks, it doesn't flow. So a time domain plot, when we're working with a map, says, what is the state at time n as a function of n? And you've seen these kind of pictures. The first return map we use when we're interested not in the details of what happens with time, but when we're interested in something about the relationship between an iterate of the map, that is a number we plug in, and what it does next. We might also be interested in the relationship between where it is now and where it will be 2 time clicks later. That's called a second return map. And we did a lot of work last week, and you did some work over the weekend with the logistic map, which looks like this. This is a one-dimensional map. A single number is the state variable here. This is a single number for x, and it has a parameter r. And again, I drew you this picture before. This is a box of mathematics called L that takes in xn plus 1 and spits out xn. And there's just a remarkable amount of richness that comes out of this, which is why we use it as an example. If you take this thing right here and you plot it on these axes, it's a parabola. It looks kind of like that. There's also this very special line, looks like that, which is xn plus 1 equals xn. So in a sense, this parabola is that, and this equal sign is that. What I mean by that is, and I showed you this operation before, you start with some x, you walk up to the curve, that's the act of evaluating the right-hand side, and then you walk over to that line right there, that's the act of setting that equal to the next iterate. And then you can keep going like that. And this is called a cobweb diagram or a return map or a correlation plot. And where you see the iterates, this is the first one. This will be the second one. This will be the third one. So really you can think about the dots as bouncing around on that parabola like so. And those are the iterates of the map. We also call that a trajectory or an orbit. On Thursday, I took this and I plugged it into itself to come up with the equation for basically L composed with itself. Oops, I got this wrong. This should be xn. Let me redo this. Sorry. Xn goes into a box that has L composed with itself, and out comes xn plus 2. This is a different kind of thing. L composed with itself is a quartic because you take this and plug it in there every place. So this is a quartic, so it has x to the fourths in it. And I drew that one for you. Color. It has 2 humps, like that. You can draw the same kind of line. Oops, I went off the edge of my paper. And both of these maps, or both of these plots, have an important property that the place where the blue parabola and the orange line and the green, whatever that is, and the orange line intersect, those are fixed points of the map. That is, if I start here and I walk up to the curve, I end up at the intersection of where I was and where I'm going to be. So that's a fixed point of the map. Same thing here. This is a fixed point of that map. The definition of a fixed point of a map is a place, an initial condition, where if you apply the map, the next iterate is equal to the same point. That is, there is no movement. You put the map there, put the system there, it doesn't move. Now, stability, I need another piece of paper. There we go. Stability is a little bit different. Stability, you need to think a little bit more. So imagine we have a logistic map. I'm leaving out the axes now. So here's the fixed point. And if I start at x star, I stay at x star. That is that x star is equal to L of x star, where L is the logistic map that I wrote on the previous slide. What happens if I'm a little bit below or a little bit above? That's what stability is about. So stability is about what happens if I poke this initial condition. Does that perturbation then shrink over time or does it grow? And you can explore this geometrically. I poke it a little bit and I get this. If I poke it this way a little bit, I get this. So these little pokes that I delivered, they shrink over time. And you can do this, I alluded to this last time, but you can think about a little ribbon of initial conditions. So I think about here's my fixed point. Let me take 2 initial conditions this far apart. So here's x1 and here's x2, and I watch where they both go. I should actually, let me do it differently. Let me do it a little bit further over. Redo this picture. Sorry. Here's my parabola. Here's my line. Maybe try here, and I'll try here. and then watch what happens. Okay, and look at the, if you color this in, you look at this thickness right here, and you look at that thickness right there. This is this thick, that gets thinner. And that's actually the mathematics of convergence, is this band, this ribbon here, getting thinner as it bounces off the curve. And what that leads to is a geometric analysis of why that happens. And it has to do with the slope of the blue thing at the fixed point, because it is exactly that slope that causes that ribbon to get thicker or thinner. If the slope looks like this, the ribbon will get thinner. If the slope looks like that, the ribbon will get thicker. That's just geometry. So that led us to that analysis of, where am I going? Of bifurcations there. Because if the slope got to be bigger than 1, that fixed point was no longer stable. And that meant that that was a bifurcation, because the fixed point lost its stability. That's a qualitative change in the dynamics. Okay, so what happens after that fixed point becomes unstable? I hope you saw this. Below that R value, if you plot in the time domain, there's some sort of transient, but then you have a fixed point that's just stable. Here I'm drawing on xn versus n. And as you turned R up a little bit, I hope you saw something different happen, which is some sort of transient, and then something like that. Oops, I got to move this up. My apologies. So here's a fixed point, because it's just a fixed point at that point. Here we've got beep, boop, beep, boop, beep, boop. That's a 2 cycle. So from a fixed point to a 2 cycle, those are 2 things I hope you saw in your explorations. And I hope you said something about changing R causes the fixed point to bifurcate into a 2 cycle, and vice versa if you went down. All right, so what happens beyond the 2 cycle is actually quite interesting. So what happens beyond the 2 cycle? I do not have to use this camera more than one more day. Let's see if I can get this to work better. Sorry. Going back to that picture of the second return map, this is xn plus 2. The thing looked kind of like a 2-humped camel. I explained the other day that if you're looking, if you're plotting a first return map and R changes, the parabola does this. If R gets bigger, the parabola gets taller and thinner. Well, what happens here is this. Also taller and thinner, but the bumps get taller, right? And look at what happens near this fixed point. You can see that the slope is there, and then it's there, and then it's there. And the same all the same ideas apply, that the iterates of this map will first do this, and then eventually they will do this, like so. And what dictates the difference between these two is the slope of the blue thing at the orange line. One important point, when you're actually doing these kinds of iterates on a plot like this, you're not seeing every iterate, you're seeing every other. So you're seeing, a fixed point in this map is actually a 2 cycle of the logistic map. So a fixed point of L composed with itself, which is this thing, is a 2 cycle of the 1-time click map. All right, so what happens when this R gets big enough so that the slope of the blue line at the orange curve gets bigger than -1, basically 45 degrees? We get a 2 cycle. So first we get a fixed point. That's first. Then we turn R up, we get a 2 cycle. And then I hope you saw this, we get a 4 cycle, and then we get an 8 cycle, and so on and so forth. So we get what's called, yell at me if I don't have the paper on the camera, please. So this is a sequence. You start out with a fixed point, then you turn up R. So this is going beep, 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 beep. And this is going beep, boop, beep, boop. And this is going beep, 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 beep. And I'm not going to try that one, but that's what it does. So 1 to 2 to 4 to 8 to 16 and so on and so forth. This should be quite comforting to a computer science audience. Okay, so lots
Wait, so
going
why
on.
does it
Yeah, what?
why does it oscillate? Because of like how it intersects the xn plus 2 graph? I'm not entirely clear on that.
Why does it oscillate? Because okay. Can you rephrase that again?
Oh, I'm just not really sure about the link between, or I'm confused about the link between, you know, the xn plus 2 plot and the like 2 cycle, 4 cycle stuff.
Ah, okay. This is a picture only for this situation. I didn't actually draw the picture for this. It would have 4 humps, and it would be, I would have to draw a return map for xn to xn plus 4 in order to make that argument. I didn't actually draw any of this. So
like how much of a cycle it has is dependent on what the like degree of the polynomial in xn plus 2.
good question. So it actually isn't. If you're not talking, could you please mute? Somebody was giggling. I'm sorry, it's a little distracting. It's okay. So it's not related to the degree of the polynomial, and I never thought about that before. It's just related to the shape of the curve at the intersection. And so the bifurcation that causes this 2 cycle to be unstable is not, or at least I don't know how that is related to the exact shape of the curve that intersects if we built the same plot for xn to xn plus 4. So I don't think there's a relationship there, but I don't know. I'm probably not helping. Did that help at all? Just, I'm saying that
Yeah.
Yeah, okay. I didn't actually do any drawing here. Oops. That broke up.
So it's more the humps of the graph than the intersection.
I don't know whose internet is broken, but you might want to turn off your video and re-ask that. Is my internet going wonky?
No, it sounds good. I have a different question though, somewhere related. So
Go
does
for
every
it.
logistic map have a 2 cycle? It's just maybe unstable or stable, we don't know.
The logistic map is a single equation, and they all have 2 cycles for a wide range of R's. And then you're actually getting ahead of the game a little bit. They also have 2 cycles that are unstable, but those are way higher up in the R range. And I'll show a picture of those. So I guess you're asking about every logistic map. So I think of the logistic map as the full equation with any value of R. So what I say is that for a range of R's, your statement is true. Okay.
There's a question in the chat, the one that you
Okay.
could hear.
If you're chatting a question, you need to say it because that's hard.
The person who had the bad internet.
Oh, I see. Okay. The cycle from the number of intersections of the graph and the line, not quite. So what you do is you make the plot for the period that you want to study, and then the single intersection between the line, the orange line and the blue curve, will tell you about that orbit. So it's not necessarily the number of humps in the graph, it's really about the intersection. And it is the number of, I'll draw another picture about the number of intersections in a second. Okay, get rid of my chat window so I can't see it. Okay, so what happens, and I haven't explained the why, I've just explained the what here, is that the logistic map, as you're turning up R, first you get the fixed point, then you get the 2 cycle, then you get the 4, and so on and so forth. That is the way it is. I haven't done a whole lot of mathematics about the exploration. Now, there's a lot going on here, and there's going to be a new way to plot this, which is a highly condensed way to plot all this behavior. Now, when we were interested in what happened, the details of what happened in regard to time, we put time on the horizontal axis. When we were interested in the relationship between an iterate and the next iterate, we put those on the two axes. If we're interested in plotting somehow all of the behavior that changes, or basically the behavior for a whole range of R's, we just put R on the horizontal axis. And that's called a bifurcation diagram. A bifurcation diagram. Try moving the camera up a little bit. There we go. Hopefully that works. Do this. So wiggy when it does that focus thing. Okay, bifurcation diagram has on the horizontal axis R, because we want to know all the different things that happen in different ranges of R. And on the vertical axis, it has what happens, the state of the system, xn. And each vertical slice of such a plot is one plot, like from problem set 1. So say this is R as, I don't know, 2.1 or something like that, is one problem set 1 time domain plot, which might look like this, with the transient lopped off and thrown out, viewed from the side. So this is my eye looking at this from the side. So here's some dots. Here's some more dots. What would I see if I look down there? I just see a whole bunch of dots at this height. So there's dot, 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 dot on top of each other. If I hadn't thrown out the transient, what I'd see is dot, 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 dot. Make sense? Okay. So this translates to that. If I go up a little higher, say to 3.1, this slice of the bifurcation diagram is constructed by taking a similar plot, time domain plot, xn versus n. And you've seen this, it's a 2 cycle, it does that. And here, we're going to again throw out the transient, and we're going to look at it from the side. And what are we going to see? We're going to see dot, 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 dot. So this whole thing gets smashed into that. Okay, so the key is make the iterates, do the iterates, throw out the transient, and look at it from the edge, and you'll see the slice of the bifurcation diagram. Now, how long the transient is, that's an issue. You can't say anything a priori about that. You have to explore that yourselves by Braille. You have to kind of throw out more and more and more transient until you see things settle down. Now, how do you do this thing? Many of you probably did when you were doing problem set 1, which means you're ahead of the game because making this is problem set 2. So how you do this is problem set 1, this is problem set 1. So basically you take problem set 1 and you wrap it in a for loop, right? Just wrap it in a for loop. For R equals something to something, do this and plot it that way. So problem set 2 for this course looks something like this. For, and you don't have to use a for loop, you can use whatever you prefer. For, I don't know, R equals 1 to say 4 by 0.01 or something like that. So I'm running my for loop from 1 to 4 at the interval 0.01. I don't know what language I'm writing in. Logistic, whatever you wrote for problem. So this is problem set 1. From, it really doesn't matter what initial condition, this is x0. For this map, it doesn't matter what initial condition you choose. For others, it will, as you'll see. Then you pass through R. And then maybe there's 1,000 points that you generate, but you throw out the first 500. And so this is the R parameter, this is the transient. And this is the number of points, number of iterates. And you can do this however you want. it can be, you can flip these arguments, you can do it however you want. You just need to be able to pick some number of points and throw out some number of points. And you can do that however you want in your code. Here, what I'm doing is I'm assuming that I will start the logistic map from 0.5 using whatever R value the for loop passes to me. I will run it for 1,000 points, but I'll throw out 500 and I'll plot the rest. And I'm going to plot it on those axes that I showed you in the previous plot. So not like your problem set 1, but you're just plotting this. Okay. Now, this is an R spacing. This is the R spacing. What this will control is whether you see something like this or whether you see something like this. Okay, so the let me actually draw this a little better. What you're going to get is going to look something like this. I'll do it. Let me do it in a fresh piece of paper. Fresh piece of paper. What you are going to get when you run that code is something that looks like this. Here's the fixed point for 1R value. Here's the fixed point a little higher. Here's the fixed point a little higher, and so on and so forth. And then eventually, the bifurcation to the 2 cycle is going to happen like that. And this spacing right here is that R spacing. Okay, this is R, X, N. So you can make the plot as coarse-grained or as fine-grained as you wish by changing that. And you can, what you should do is make sure that you are seeing dots here and not something that looks like this. So you're not seeing, you're seeing a single clear dot like that. You're not seeing dot, 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 and then the dots, all the dots on top of each other. Because what this means is you've plotted a little bit of, oh, I shouldn't make that like that. You've plotted a little bit of this. You haven't cut off the whole tangent. You've started plotting here. So you're seeing dot, dot, dot. You want a nice crisp dot. So you want to throw out enough transient so you see a nice crisp dot for the fixed point. So this is what you should see. And what's going on, and if you go a little further, you'll see something like this. So if I were to draw it in curves, which I shouldn't, but just to make it easier on myself, there's this, and then it splits, and then it splits, and then it splits, and so on and so forth. This is a 1 cycle, 2 cycle, 4 cycle, 8 cycle, and then it keeps going. It's called a period doubling cascade. Period doubling cascade, or a period doubling bifurcation sequence. Bifurcation sequence. Okay. And each of these things is a bifurcation. So that's a bifurcation. Sometimes these particular ones are called pitchfork. Pitchfork bifurcations. They're also sometimes called flip bifurcations. They're also sometimes called supercritical flip bifurcations. People that study these bifurcations love to give them really fancy names, and different people give them different names, and we're not going to talk about this at all, but just be aware that these things do have different names having to do with the mathematics of their creation, which relate to the questions that were asked 5 minutes ago. And we're not going to get into those too much in this class because they're pretty esoteric. But anyway, you can think about this. It's obvious why it's called a pitchfork, because it looks like a pitchfork, except it's missing its middle tooth. So pitchfork bifurcation. And I purposely drew these getting smaller. You see, there's this big wide one, then there's a littler one, and so on and so forth. And that is actually something really deep. And it goes to something proved by Mitchell Feigenbaum regarding that sequence. And what Mitchell proved was that there is a constant ratio in the widths of these things. And it's 4.667 something or other. That is, if you look at this width right here, and call that delta 1, and then you look at this width right here and call that delta 2, and then look at this width right here and call it delta 3, and you keep going because there's more of these that get littler and littler. It is the case that delta n over delta n plus 1 is equal to 4.66 something or other. I can't remember the rest of it. That is, this is 4.667 times as wide as this, which is 4.66 times 7 times as wide as that, and so on and so forth. There is technically a limit in here as n goes to infinity. I'll put that in parentheses. What this means is that it is the case that delta 1 over delta 2 is close to 4.667. Delta 2 over delta 3 is closer to 4.667, and so on and so forth. That is, this ratio is okay out here, but it gets better and better in here. That's what this is. So Feigenbaum proved this. I'll get back to PowerPoint. And he proved it for any function with a quadratic maximum. So I'm back on my PowerPoint slides now, if you're flipping back and forth. So the Feigenbaum number of 4.66 whatever is universal across a class of functions. Get my cell phone there too. There we go. So Feigenbaum's result is not just for the logistic map. It's true for any 1D map that has a quadratic maximum. What does that mean? It means that if you like that, those blue things that I was drawing on my return map, the map that you're thinking about, if it has a bump, if it has a maximum, and near that maximum, it looks like a parabola, Feigenbaum's result applies. Now, this is true for 1D maps, okay? 1D maps, we'll get back to that. But the reason that this is pretty cool, and of course, I think it's in Steve Strogatz's book, he gets really excited about this, and he says that the Feigenbaum number is a new natural constant. It is as fundamental to 1D maps as pi is to circles. Now, why are we all getting excited about this? Because in nonlinear dynamics, the field is, the mathematics is hard. There's not a whole lot of generality that we can prove. So the fact that you can generalize this result across a class of things is actually something that gets us all excited. It is a piece of the universality in chaos. And there's other universalities in chaos. The fact that it looks the same, whether it comes up in biology or chemistry or physics or my computer or whatever, that's cool. This is another piece of that. So this goes well beyond the logistic map. It's true for the sign map. It's true for the tent map. It's true for any map that has a hump that looks kind of like a parabola. And the proof is in Strogatz. For those of you who are mathematicians, you might find that interesting. For computer scientists, you might not. It's about it's renormalizations and convergences of series of functions. This is optional for optional reading, but again, the mathematicians in the room might be interested. Okay, so these little pitchforks get narrower and narrower and narrower as you turn up R. At a certain point, if you divide anything by 4.6 enough times, you get to 0. So in the limit, as n gets bigger, delta gets smaller. I wish this camera would just stop doing that. In the limit, as n gets bigger, the width of the pitchforks gets to be 0. That's called the accumulation point. And after the accumulation point, or the accumulation point flags the onset of chaos. Okay, so the onset of chaos. what chaos looks like on the axes that we were drawing on before, and you've seen these pictures. Here's the time domain. You get some sort of chaotic fuzz, but it's not quite fuzz. It's not random. It's got some structure. It's got maybe some gaps. It's got some places where it's denser. It got, maybe you see this little kind of motif repeating a couple of times. So there is some structure. If you look on the first return map, +1, here's the parabola, the underlying parabola. I'll draw it really softly, but the chaotic fuzz kind of fills up parts of this parabola. You've seen this, I hope. Similarly with the second return map, it starts to fill in the two-humped thing. On the bifurcation diagram, it's a slice through the bifurcation diagram, and you'll see all of this stuff. Again, you throw out some transient, you look at this from the edge, and you see this fuzz over here. But again, some places it's dense, some places there's none of it, some other places it's dense. And that's what this looks like. And you saw this. At least you didn't see this. Maybe you didn't. So what happens if you run that for loop and make this plot for r equals 1 to 4 with the...
Just scoot the paper up just a little
Oh,
bit. Sorry.
yes, thank you, thank you, thank you. Sorry. I will try to do that. My apologies. Why don't I'll try and get this up a little higher. And that will hopefully, I can't do this cheap camera. Yes, thank you. I'll try to not mess that up. Anyway, so what happens if you do this for a range of r equals 1 to 4? You get this really beautiful thing. It looks like that. Oops, back up. All right, this is the solution to problem set 2. Okay. Ignore these little faint lines. That was something else I was playing with, so don't pay attention to those. But you can see what's going on here. And here I've got, by the way, I've got an R spacing that's really, really narrow. So this looks like a smooth curve, but it's not. Here, from here to here, here is this period doubling bifurcation sequence, or this period doubling cascade. Here, the map has a fixed point. As we turn up R, here there's a bifurcation, and the fixed point goes unstable. It's not gone, it just becomes unstable. And a two cycle is born. And then that 2 cycle gets kind of wider and wider and wider. And here is another bifurcation. By the way, this is directly over that. These 4 things, this little piece of black, this little piece of black, and this are all a piece of the same attractor. This is not 4 fixed points. It is a 4 cycle. All 4 of those things are pieces of one particular big thing. And here, unlike my drawings, you can see that the width of this thing and the width of this thing, you can probably, if you measured on the screen, you could see that this width is 1 over 4.66 times this width. So we have a period doubling cascade at low values of R that has the Feigenbaum number ratio in terms of its length. That's this first bullet here. Then, after a certain point, when you raise R enough so that the width of these little pitchforks gets to be 0, you have the accumulation point. And after that, you get this chaotic fuzz. And I'm using the word fuzz colloquially. It's not random fuzz, it's structured fuzz. That's what's cool. So we get chaos, which looks like fuzz. I'm sure that most of you, if not all of you, when I put up this picture, you noticed these veils right here. There are all sorts of veils in the structure. What's going on here? These are the places, remember I said that in some places the fuzz is dense. This is the place where the attractor is really dense. That is an iterate of this value of X, and cursor keeps going away, my apologies. An iterate of this value of X will come back pretty close, and then it'll come back pretty close, and then it'll fall away. And I hope you saw this in your results, that you saw something that looked like it was periodic for a while, but then it became chaotic again. That's what these things are. And they have a formal name. So they're almost periodic orbits, but they're not quite. They are what are called unstable periodic orbits. And we'll talk about them a lot. They're really cool, and they happen to be part of the structure of any chaotic attractor. So that's what these veils and bands are. There are also windows of order within the chaos. Look at this thing right here. When you get up to R equals about 3.8 something or other, all of a sudden you're turning up R and you're turning up R and you're turning up R, and it's chaotic and chaotic and chaotic. And all of a sudden you pop out into a window of order. So for that value of R, the logistic map is periodic. And it's periodic with period 3, which is going to come back on Thursday. And these windows of order have their own little period doubling cascades in them. So here's a 3 cycle, it bifurcates to a 6, which bifurcates to a 12, all following the Feigenbaum sequence. So this thing here, and I actually, hang on, let me move this, there we go. Here's the 3 cycle, and then for a little bit higher, there's 6, and then 12, and so on. So windows of order within the chaos complete with their own period doubling cascades. And then the last point I wanted to bring out about this plot is that it is a fractal. It is self-similar. That is, if you took this little chunk of it, it would look like this little chunk of it, which would look like this big chunk of it. So you can drill in and drill in and drill in and get smaller and smaller and smaller. And all these things are bifurcation diagrams. They might not look just like the original, because the original, you can see it's not perfectly symmetric, but the idea is there. So it is a self-similar object. It has small copies of itself embedded in it. And then there are all sorts of other interesting things going on that we're not going to get too much into, like this point right here. I keep having to move my Zoom window. This point right here, the special things that happen there, it's called the Miserevich points, and mathematically it's quite interesting, but we're not going to mess with it too much in this class. There are lots of other maps that have really cool bifurcation diagrams. I've got one up here. And what's going on here? So they've got a map here. They've got slightly different notation. Instead of xn, they just use n. And they've got an r parameter. I don't remember what they've got it set to, but this number is going to change. And this is a bifurcation diagram constructed for this value of this number. And here is the value for r, okay? So here's r. And this is what the bifurcation diagram looks like for this particular version of that map. And what they're going to do is they're going to sweep they're going to sweep this. Right, so pretty cool stuff. But similarly, here is a period doubling bifurcation cascade. Here's chaos, here's windows of orders within chaos, and all that same kind of stuff. Let me get out of Safari. And here is the long, nasty link for that, but it's also posted on the course homepage if you want to play with this Reddit bifurcation diagram. And what's amazing to me, or what was amazing to me when I first saw this, and it still is that this picture is simply iterates of the logistic equation. Okay, it's just iterates of this really, really simple map for different values of R. And it's incredibly complicated and incredibly cool. It's also a great example for this class, the logistic map is, because it has all the kind of standard symptoms and challenges and issues that they're involved with nonlinear dynamics. It has attractors, it has basins, it has fixed points and limit cycles and chaos and sensitive dependence on initial conditions, and all that cool stuff turn up in this very, very simple example. All this is in a one-dimensional map of the unit interval onto itself. This is not a partial differential equation. You don't need to be complicated to be chaotic. And
can we read anything into the density of the colors aside from the veils themselves? But in the previous example, there were some darker hues there, and then also here.
Yeah, good questions. I have no idea how they were color coding that yellow thing, but in my plot here, the color, the denseness really comes just because there are more points. So the denseness means that the the trajectory is running around in the snow, and there's some places where there's leaving more tracks in the snow. Now, actually, that's a really good question, because how much of this structure you will see depends very much on how you choose how many points you plot. Because if you choose to plot 10 million points, you're going to get a great big blob of black ink, right? No matter, because it's chaotic attract, I mean, there'll be a gap. So like this one, if you plotted right here, you wouldn't get a blob of black ink right here. But if you plot too many points, all these points are going to bleed together. So you're going to have to be careful with how many points you remove. If you remove not enough, there's going to be transient. If you don't plot enough, you're not going to see the structure. But if you plot too many, you're going to have, and this is, by the way, an important point is not to use great big icons for your points in this class, because if you use a great big blob of ink to plot where something is, then if there's another point right that's this close to it, that's going to just look like a big blob of ink. So the denseness does here imply something about the denseness of the attractor, that is how close the threads of the attractor are, as it will. But all of that hand waving was to say that you got to be careful when you're making the plots to actually see that without obliterating it. Does that help?
Yes, thank you.
Okay, good. All right,
I got a question as well. Oh, sorry.
go for it.
So like technically you said initial condition doesn't matter, but this is kind of an edge case. But if it was an unstable fixed, if you had the initial condition as the unstable fixed point, technically, so that's a really edge case. Sorry to say that.
No, you're absolutely right. And that's a really good point, because if I happened to balance my initial condition perfectly on one of these unstable things, if I was perfect, it would stay there. That's a really good point. So if you were at this state right here, where there is actually, so what if I were to pick that initial condition absolutely perfectly? It would stay there. You're absolutely right. That's an interesting edge case. Yes, good.
I have a question too, which is, do we define chaos based just on initial conditions, or also sensitivity to the parameter value R? Because it seems like in some values R, this system wouldn't appear chaotic because it's, no matter the initial condition, approaching the same fixed point, or the same period cycle, whereas in other conditions it does appear chaotic.
Yeah, no, these are really good points. So it's semantics to some extent. We say that a system, the same system can be chaotic for some parameter values and not chaotic for others. So just saying that it's a chaotic system is really kind of being a little bit sloppy. What you should say, but we don't, is this system is chaotic at this parameter value. That's one piece of the answer to your question. The other piece of your question is also very astute, which is that a system can be chaotic for some initial conditions and not for others. In this particular system, that's not true, modulo the edge case that was just brought up. That is, any initial condition that doesn't happen to land perfectly on one of these very special things will go to the chaotic attractor for that range of R's. But it could be the case, and you'll see these in other examples later in the class, that the same system is not just chaotic for some parameter values and not chaotic for others, but it could be chaotic for some initial conditions and not others. So that was a complicated answer, but the answer to both of your questions is you have to specify. Okay, is that all right?
I also have a follow-up question.
Mm-hmm.
So here, for example, right before the first bifurcation, we also see some light lines. Is it because the removal of the transient is not clean enough?
No, the light lines here are something completely different. I should have taken them off the plot, but it was a pretty plot, so I used this one. So the light gray lines are something completely different. Yeah, I will redo this plot so it's not confusing. Okay, so again, universality. Many of the proofs and properties here depend only on the quadratic maximum, but it's important not to take this too far. If you go back to this slide, the Feigenbaum number holds for any 1D map, okay? This does not say 2D maps. It does not say 2D flows. It only applies to discrete time dynamical systems that have a single state variable. That is not to say that it may not be true for other things. That is, it might be, you might see a period doubling bifurcation sequence in a 2D map. It's just that Feigenbaum's proof doesn't hold. That's all. So there is some evidence that the Feigenbaum result holds in higher dimensional maps. There is some suggestive results that say that it holds in continuous time dynamical systems or flows. It's just that the proof doesn't extend there yet, at least. Okay. So I'm going to actually draw a few more return maps to reinforce some intuition that will help with some of the questions that came up. Anyway, and what I'm drawing here is, this is not the logistic map. This is some other map. It's the same kind of plot. It's a first return map. But the thing itself has a completely different shape. So this is, again, not the logistic map, but instead something that looks, I'm going to draw this a little carefully. I'm cheating a little bit, but there we go. All right, so we got 3 interesting points. And so this is some f of x n. These 3 points still mean the same thing that we talked about before. They're still fixed points in the sense that if I started right there, or right there, or right there, started at any of these initial conditions, and walked up to the curve, I would just stay there. Okay. But we can do some interesting experiments here to study their stability. So first of all, let's start here. You see what happens. If I start here, that looks like it might be a little 2 cycle. I didn't do a good enough drawing to do this, but let me try this here. Okay, that's better. So this is a fixed point, and this is a fixed point. What about here? Okay, see, if I start here, I'm going to end up there. If I start here, this drawing's getting kind of messy. Apologize. All right. So go through those in your mind and think about that. I'm going to redo the drawings so that I have a bit more space and a bit less clutter. It's my map. That's not going to work. Well, allow me to cheat and have my diagonal line not be perfectly diagonal. And let's think about this. So right here, that's initial condition 1. That's going to be a fixed point. But if I move over a little bit, over to here, if I move over to here, yeah, there we go. So this thing here is an unstable fixed point. Fixed point. I'm going to do FP for fixed point. And these two here, these are stable fixed points. That's a stable fixed point, and that's a stable fixed point. Stable fixed points. And these fixed points, these stable fixed points, have basins of attraction. Remember what that means. That means all the initial conditions that go to that fixed point. So let me color code these a little differently. So let me take this guy and make him this color and color code on the horizontal axis all the initial conditions that go to that. So this one did, and I could do that. I could do this whole set of points right here. If I tested all of them, these would all go to this fixed point. But let's take this one and make it blue and color code all the initial conditions that go there. Well, this one is, and if we tried here, it would go there and here. And so it's all these points right here go there. But watch what happens here. Watch this. Here, let's try this point right here. Look at that. So this point over here should be color coded red. And indeed, you can figure out that basically everything to the right of this point right here will head over there. So this blue goes up to here. And it goes right up to there. And this red goes right up to there. So if I were to magnify this out, there's the red comes up like this. And the blue comes up like this. And they don't quite touch because there's a point in the middle right here, which is not in the basin of attraction of either of those fixed points. Okay, so this point right here is the continental divide. Here's the terrain to the west of the divide. Here's the terrain to the east of the divide. But over here, there's something else going on. This is weird. This says that the basin, so here is the basin of attraction. This is the basin of attraction of, I'll give this guy a name, X1 star. Let's call this X1 star. And that basin has two separate pieces that are not connected. And that's weird. Okay, so basins of attraction in maps can be disconnected. And that is not the case in flows. Because in a flow, you have some sort of an attractor, call it V or whatever. It lives in the bottom of a basin of attraction, W. And any initial condition from anywhere in W, and W includes V, by the way, so this is an initial condition in W. Any initial condition from anywhere in W has to have a smooth path available to it for the trajectory to run down to V. Again, so the raindrop has to be able to run down to the ocean somehow. Doesn't mean there can't be a hole in the basin, because this thing can go around the hole and down there. But it cannot be the case that there is an attractor living in the bottom of a basin W that has another piece way over there. That cannot happen. Not allowed. So basins and flows have to be connected because the initial condition needs to be able to run down in continuous time to the attractor. And here it can't do that. It can't, there's no way a continuous line can hop across there. In a map, it can hop because in maps, the state goes hop and then it goes hoink and then it goes hoink. Basically, it can hop over things. That's a formal statement of how this works. So basins and flows have to be connected. Basins and maps do not have to be connected. And we'll come back to that a bunch of times. I wanted to show you one other really cool example of this stuff, which goes back to a method that probably all of you have seen, Newton's method. Newton's method is perhaps the most famous common method for solving a nonlinear equation. So if you have an equation, f of x, and you want to know what x makes that true, that is a root If you want to know the roots of some nonlinear equation, this is your baby. That's what they teach you. And the way it works, many of you have seen this. What it does is it does this business of walking. It takes the tangent of the curve and it extrapolates and so on and so forth. That doesn't really matter from our standpoint, because what we're interested in is the fact that Newton's method is a box of mathematics, let's call it N, that takes a guess at a root, and it gives you a next guess. Newton's method is a map. It's an iterative map, and the iterations are that tangent nonsense that's in there. So let's think about a particular example. Let's think about a particular nonlinear equation, and we want its roots. Now, of course, it would be kind of silly to use Newton's method on this, because this is a pretty easy thing. You can just figure out the roots by inspection, and applying Newton's method to that would be kind of like using a sledgehammer to kill a fly or something like that, because we know what these roots are. The roots of this equation are plus and minus 1 and plus and minus I, or if you're an engineer, you call that J. I'm not sure why. So it has 4 roots. That's because it's a polynomial of degree 4, and plus and minus 1, plus and minus I. And if we drew those in the complex plane, this is the real part of, let's do X. And this is the imaginary part of X, where X, N, that's the guess. The roots are here, 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 and here, okay? 1, minus 1, I, and minus I. Those are the roots. And what Newton's method is designed to do is, given a guess like that, Newton's method is designed to produce some sort of iteration sequence that pulls that guess towards one of these roots. It might not be nice like this. It might go hoink, hoink, whap, 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 like that. Because again, in maps, you can jump in state space. Flow, you can't. So Newton's method, again, is a map, and it has a particular purpose. From our standpoint, it just means that whatever initial condition there is at that point in the space, the iteration sequence is going to eventually converge to one of those roots. What does this look like? Go back to my PowerPoint, because this picture is gorgeous. That's what it looks like. Right? This is beautiful. This is from James Gleick's book Chaos, and what he's done is, here are the 4 roots. This is minus I, this is 1, this is plus I, and this is minus 1. And he's color coded all of the initial conditions that converge to, come here, all the initial, let me say it first in numerical methods language, all of the guesses that Newton's method causes to converge to this answer, this root, are color coded in red. From our standpoint, these are initial conditions that, under the influence of the map, which is Newton's method applied to x fourth minus 1 equals 0, converge to this fixed point. These are fixed points of the map. And that's important, fixed points of this map. Because if you plug in the answer, the guess 1 to Newton's method will say, I'm done. I'm not going anywhere. I'm staying right here. That's a fixed point. So this particular map, Newton's method, wrapped around that particular nonlinear equation, has 4 fixed points, which are the roots. Now, interesting what he's done. By the way, the darkness here is how fast it converges. So these numbers right here get to the root really quickly. The lighter colored red get to the root more slowly. And there's all sorts of coolness here. Like, who would have thought that, this converges faster than that? What's going on? Anyway, or sorry, the other way around. This converges really fast, but it's further away from the root than this is. So again, lots of interesting stuff. These diagonal lines, it actually makes sense that these would be in some sense dividing lines between the influence of these different fixed points on the kind of the pull of the dynamics, the pull of the intent of Newton's method to find the roots. Because if you start kind of halfway between 2 of the roots, in some sense, the pull, as defined by the tangent that lives in Newton's method, could be pulling you in both directions. So it makes sense that there's this kind of diagonal dividing line structure in this thing. But what's really cool is the amount of complexity that is braided onto those dividing lines. If you were to drill in really closely to right here, you would see that this piece of red is completely surrounded on all sides by other colors. And this piece of yellow is surrounded on all sides by other colors. So this is like the picture that I drew before, where you have a piece of the red basin of attraction over here and another piece of the red basin of attraction over here. They are not connected. These basins of attraction are not connected. There is red and green and blue infinitely interwoven as at every possible magnification scale along these diagonal lines. So the basins are not connected. There are places, there's all sorts of red pixels here that are in no way touching any other red pixels, and that's true for all colors. And indeed, like the bifurcation diagram of the logistic map, this is a fractal, so that the code word there is, if you drill in, you keep seeing. That is code for fractal, as we'll talk about next week. So amazingly a complicated thing, which is really pretty cool. So questions on this before I'm just going to set some stuff up on stability for next time before we quit. Questions on this? One point I did want to make is the people who designed Newton's method don't really want the results to be complicated and interesting. They just want an answer, right? So numerical methods are designed to give people answers to problems. You don't want them to be interesting. You just want them to give you the answer. And this is part of what's really different about this course from the applied math version of this course, which is that our observing tool, our experimental tool, our laboratory is the computer using a numerical method, using a variety of numerical methods. And the numerical methods, depending on how they're implemented, depending on the parameters that are inside that implementation, can really do wild things. And that is actually kind of upsetting. If all you want is the answer, you don't want interesting things on the way to the answer, you just want the answer. An analogy that I also often use for this is, imagine the Hubble Space Telescope. It's pointing at a quasar or something like that, and it turns that quasar into a planetary nebula or something like that. These are both things that are interesting that people use the Hubble to look at. Imagine if the observing instrument caused one to turn into the other, to cause one to look like the other. Well, that's what ODE solvers can do. An ODE solver, depending on the parameters of its implementation, can take a fixed point and make it bifurcate into a limit cycle. That the ODE solver should be giving you the picture of the fixed point. It gives you instead a limit cycle. And this is very, very interesting, but it's also kind of dangerous because, again, these are both things that you would expect to see in the kind of system that you're playing with. And you don't want your observing instrument to change one into the other. So numerical methods, again, they can mess with you and you don't even know you're being messed with because they're both kind of expected things that are turning up. They're just different expected things. This is why I really, 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 really want you to write your own code, because only when you write your own code do you have access to changing these kinds of parameters. And only when you mess with this and you get bitten by it will you really respect what's going on here. So for example, those of you who know a little bit more, and we'll all get into this, you change the time step for the solver, you completely change the dynamics of the result. This is upsetting, but it's good to know about. And we'll come back to it over and over. But first, I'm just going to set this up for next time. I want to do a little bit more mathematics about my hand waving, about the little ribbon getting thinner and thinner and thinner. And so I want to dig into just a tiny bit. I'll just set this up today. Let's get this over to Zoom and set this up into this notion of this hand waving about what does it mean for something to be stable? the words I've used are, well, you poke it and the perturbation either shrinks or grows. That tells you whether it's stable or unstable. So let's dig into this. And this is going to take us to Taylor series, which you may, hopefully you remember at least the name of. Taylor series help you if you know something about where something is, and you want to know something about what happens near that something. That's where Taylor series helps you. And that's exactly what we're after, because we have a point in the space and we want to know what happens to a little perturbation near that point. So here's just a bit of math. So let's say we've got X star, and it's a fixed point of some map, I don't know, call it F. That means that X star is equal to F of X star. Okay, if X star is a fixed point of some map F, then you chuck X star into F and you get X star back. That's the definition. So we perturb it. That is, we make a little change to X star, a little delta X change, and we want to know what happens. To that, that delta X. Okay. And so what we want to know, and actually as a first step, we want to know what happens, I should say, we want to know what happens to F of X star plus delta X, because eventually we want to know what happens to the perturbation. But the first thing we do is figure out what happens not to the trajectory, but to the perturbed trajectory. And this is where Taylor series comes in. So that's xn plus 1. So what happens next? So xn plus 1, we know the equation, and we can approximate, this should be an approximating with Taylor series, and you've probably seen this. Okay, and then there's some, I need a delta xn here, and then there's some other stuff. There's some sort of order delta xn squared term, plus there's some higher order terms. This is the Taylor series. And you know when someone does this, they're going to neglect it, and they're probably going to neglect that too, and I'm going to. Okay, so this is what happens to this. That's what happens to X star plus delta X. If I just want to know what happens to delta X, so what is delta X's future? I want to know that. I have to subtract off f of x, because I know where this goes next. I want to know what happens to this. I subtract that off. So delta x at the next step is approximately equal to f prime x star times delta xn plus that stuff that I'm just kind of waving my hands about. I'm going to neglect that. I'm going to neglect that. And by the way, this amounts to linearization. And I will leave you with the thought exercise that I'll pick up on Thursday of looking at this and thinking about the geometric argument for the stability of the fixed point. And I will pick this up with you on Thursday, and that will be, thank God, our last day with this obnoxious document camera, and with everybody else being this big. And I really hope they don't change their minds and flip us to remote after this weekend as well. But I will see you all on Thursday in this format, and then hopefully Tuesday in real life. So thank you. And I'm going to stop recording in case there are questions. There we go, stop recording.